Hello, this is Sean Mullery from Electronic Engineering at IT Sligo. And earlier I set you an assignment to try and figure out how we would actually take note of the actual frequency of the signal that was coming in on port RA4 rather than just reporting how many cycles had passed during 1 millisecond. So I have the program here that we used previously, and what I'm going to do is I'm going to add just one line of code. But before I do that, I want to report some things to you. I want to take note of something before I do so that you're aware of the implications of what we're about to do. So I'm going to run the program firstly, and I'm going to take a look over here at the amount of information that's used in RAM and in Flash. Now, we can see here that the RAM usage, and you can take note of this with a pen, is 391. And it's using 3%. Okay. Now in Flash we're using 4096, or I think 4096 is the full amount. Let's just see here. Oh yeah, no, 4096 we seem to be the amount of words that we're using. No, it's not. Sorry, it's the number under it. I knew I was wrong there. And that's the total number that we have available to us, and we're using just 71 of those. So I would assume with the RAM it's the same, that 391 or so is about the height of what we can use. Instead we're only using just 10 there of it. Okay. Yeah, in fact if I just pull it over here further this way, I couldn't quite see it here, we can see the amount that's free there is 381 free out of the 391. And in the Flash, which is where our program memory is stored, we're using 71 out of the 4096 available to us. So that leaves us with 4025 free. Okay, so remember, Flash is where our, in this particular case, is where our program, the size of our program is going to be held. RAM is the amount of information we need in order to be processing data on the fly. Okay, so remember those numbers there, just take note of them, how much we're using. As you can see, we don't seem to be using a whole lot, but that's because our programs are indeed very, very small. When we get up to larger programs, it can become difficult to try and fit things in the space, so we need to be careful of that, and therefore we need to take all necessary precautions. It's never a good idea to start doing things that are going to take up huge amounts of space, because we don't know at what point we're not going to have enough. So how am I going to, if you recall last time, if the thing, if there were 10 cycles within 1 millisecond, that's what we reported 10. But if there are 10 cycles in 1 millisecond, and there are 1000 milliseconds in a second, to give the number in hertz, what we should do is we should take the number and we should multiply it by 1000. Okay. Now, of course, you could use the TMR0 for this either to do it, but the fact is that one way or the other, we're going to end up multiplying two numbers together that are, or at least one number, and then putting the result in a number that is a 16-bit integer. And the problem with that is that this is an 8-bit microcontroller. And 8-bit microcontrollers, while they will do things that are 16-bit, they don't do it easily. They effectively have to do it in software. And that takes quite a bit of processing. So what we're going to notice when we run this and we look at our figures again is that our figures have changed. Okay, so we're running there. Let's have a look at the detail here. So if you remember previously, we were using 3% of the RAM, and we were using 3% of the RAM. We were just using 10 bytes. We're now using 16 bytes. So a little bit of an increase there straight away. What we also then notice is that in terms of the amount of flash we're using, last time we were using 71, now all of a sudden we're using 127. We've gone from 3% up to 4%. So from 71 up to 127 seems an enormous jump for just one line of code. So the question is, what exactly is happening there? Why is that occurring? So what I want to do is I want to set a breakpoint in there just at this point. Now we'll notice, by the way, that we can see that the frequency is 10,000, which means that it's 10 kilohertz is the signal. So that all seems to be working very nicely. And if we test that again and again and again, You can see sometimes it comes out at 11,000, which is a little bit worrying that it's counting a few more of them than I expected. But anyway, that's not to be too concerned about for the moment. It's not what I want to show at the minute. Well, of course, sorry, it would be 11,000. I am correct in that, because if you remember last time it was coming up as either 10 or 11, and we're multiplying that by 1,000. So it's not quite the same thing as I was saying to you before. If we measured it for 10 milliseconds or so, that would give us an improved response. So that's the reason. So we can see that small error, it's still there. That 10% error is still there, and we would have to avoid that by having a longer timer 1 slot. However, that's not what I want to show you for the moment. What I do want to show you is what actually occurs with this particular line of code here. So I've put a breakpoint just before it so that we could then step into it afterwards. So this is what we use to step into something. So I step to the next line and then I step in. And what we see is that it's jumped to this function that you won't have seen before. It's in the wmul.c file, not one we've seen before at all. It's one that comes with the libraries. And this is dealing with the situation of when we're multiplying two unsigned integers by each other. Okay, and because integers, or the unsigned integers, are ordinary integers, are 16 bits, that's not native to this microcontroller, because the microcontroller is natively 8-bit. It has to actually call a function to multiply those and do all sorts of manipulation. And you can see you've got the multiplier and the multiplicand. And the different manipulation that it's doing, it has to go through a do-while loop, which is a slightly different version of a while loop, and it has to run through that a number of times, basically until the multiplier becomes 0. So it has to run through that quite a number of times in order to do its job. This means a number of things. Firstly, it means that all of this is code memory, and since it's all code memory, that all takes up the extra number of bytes that bring us from 71 up to 127 in our code memory. We'll need some RAM in order to deal with these, the multiplier and the multiplicand. So therefore, we're going to have an extra bit of RAM there in order to deal with that and to deal with the return type that's here. Okay, so we have to deal with all that. But the other thing as well is, this can be a little bit deceptive because it shows a while loop, but we're not entirely certain how often that while loop actually runs. Now we've got a multiplier here. Okay, so depending on how big that number is, then we can clearly see that it's the size of that number in binary. We can see that we're shifting down by 1 each time here. Okay, so the number of binary ones in that, once we get to a situation where that's 0, so in other words, if it's a small number, we're only going to run a small number of times. If it's a large number, we're going to run a larger number of times. Bear in mind that that is all happening inside in an interrupt. Interrupts we like to keep very, very short, and it means that that time is all being spent inside in our interrupt. And even if it wasn't in our interrupt, it's somewhere else in our program, it's taking up time. We think, by looking at our interrupt function, that that is just one quick line of code. In actual fact, that's taking a huge amount of time compared to everything else. So it's slow, it uses up more RAM, and it uses up a lot more code memory. Okay, but it does do its job. Which is fair to say. However, what we're going to do is I'm going to show you one mechanism that you can use in order to be much more frugal with your memory and be much quicker with how you operate. And this is one of the big advantages that C has over many other languages, is that we can write code that is very, very efficient. So what I'm going to do is, instead of multiplying it by 1,000, I'm going to look at what's the nearest power of 2 to 1,000. Okay. Now, hopefully, you know off the top of your head that we go up 2, 4, 8, 16, 32, and so on. We eventually come to 512, and then the next one above that is 1,024. Okay. So 1,024. I'll just write a little comment here. Is 10 to the power, I'm going to use the little power thing here, even though that doesn't work in C, 10 to the power of 10. In other words, it is 10 bits in size. So what we can actually do is we can take the frequency value, whatever it is, and we can shift it by 10 places. Remember, if I shift something by 1 place, I've effectively doubled it in size. Okay? And we know that because if we have something like, and I'll just show another example here, if I have 0001, okay, and I shift it by one place, it becomes 0010, which is a value of 2. If I shift it by another place, it becomes 100, which is a 4. So we can see that we double it each time we shift by one place like that. So if I shift by 10 places, I'm going to effectively multiply it by 1024. That's not exactly 1000 as we're well aware, but it's not far off. Remember, with the other little thing that I did of only measuring for 1 millisecond, we already have a situation where we could be out by 10%. We should really fix that if that's what we're going to be dealing with, but it really depends on the type of signal that we're dealing with. In this case, the difference between 1000 and 1024 is just 2.4%. Okay. As well as that, there are mechanisms that you could use in order to try and fix that. In other words, bias it the other way. And so what I'm going to do is I'm going to give you an exercise to try and figure out how you could manipulate the rest of your program in order to make sure that you undid the fact that we were now multiplying by 1024 instead of 1000. I want you to try and fix that without changing this number to see if you can get that right. Now, aside from that, what I want to show you is what effect this has on the RAM and the flash usage. Okay, so what we notice here with regard to the flash usage is that we are now using 86. Remember, our original one was 71, we've gone up to 86. That's not completely crazy, it's gone up by just 15 bytes. Okay, instead of the 127, which is what we were using the other mechanism. We can see that the amount of RAM has not changed at all, and that's because we don't have that whole function. We're not having to use any extra RAM in order to do the particular job that we want to do. As well as that, that section of the interrupt should run much quicker because we now don't have to go several times around a loop. That instruction of doing the shift by a certain number of places can generally be done in 1 or 2 instructions, assembly language instructions, and so therefore that can be very, very efficient as regards to the speed that something operates. So whenever you're dealing with an embedded system, firstly, it's usually best, if you can avoid it, to not use numbers that are not native to the microcontroller. This is an 8-bit microcontroller, so it's quite restrictive to try and keep everything as 8 bits, but that would be much faster. If you can't do that, the other things that you can do is you can try and only move things by a power of 2, such as we've done there, rather than trying to multiply things. And dividing things is even worse, okay, with regard to the amount of manipulation that has to be done. Okay, so we can see the benefit of doing that particular mechanism in order to actually achieve the exact same thing as what we want to do, but we'll find when we run it that we're not getting exactly the right sort of a result from it. Okay, so I'm just going to change this frequency here to change this display to decimal. Okay, and you can see the numbers that's coming out is 1,200 or 10,240, which is 10.24 kilohertz. So what I'd like you to do, and I'll be giving you this in the next exercise, is seeing if you can make a slight modification to the program in order to bring that back to being the right value without messing up the fact that we've managed to be much more efficient in this particular case. Okay.